Okay, so hello and welcome. We're looking at the maximum gap now. Let's get right into it. So the question, I already opened it here. Didn't read it yet, but opened it. Is, let's see. Okay. Maximum gap. Let's see. Given an integer array nums, return the maximum difference between two successive elements in its sorted form. If the array contains less than two elements, return 0. Write an algorithm that runs in linear time and uses linear extra space. Okay. Alright, so we can do linear. Linear time and linear extra space. Okay, what's the question? Integer array nums return the maximum difference between two successive elements in its sorted form. The array contains less than two elements, return 0. Write an algorithm that runs in linear time and uses linear extra space. So we are going to use extra space for this. Okay, I was thinking we could just take the difference. For some reason, I was thinking the difference array, and I don't think that's the right thing to do though. Maximum subarray sum, or yeah, maximum subarray sum after taking the differences. That's the solution. No, I don't think so. Maximum difference between two successive elements in its sorted form. So that's really interesting because I am aware of how you can take, like if you, yeah, I know a way to do that in n log n time. Pretty interesting question. This is a really good question, really good algorithmic question. I've thought about this question before and I came up without the answer. Oh, this is a good one. This is one that should be like kind of a gimme though. Like I should be able to do this in 5 minutes, kind of a deal. But I actually don't know it. Well, you know, I think you can do. They actually said you could do this with linear extra. You might be able to use like a DP solution, of some kind. Like let's say, I don't know. All I could think of is quadratic time. There's definitely linear, n log n time would be sorting it first, but that would be no extra memory. Quadratic time would be similar, not sorting it, just compare one number to all the other numbers, right? Find take all the differences. Linear time though is challenging, man. That's a good question. Trying to find it's the maximum between two elements that are next to each other in linear time. Linear time and linear extra space. I think I've done this before, but I'm struggling a bit. Let's see. Well, okay. I don't know. I really don't know. Linear time, huh? Well, maybe you can use a hash set for this. So what you could do is you could take each number and hash to that number I guess the best difference you've seen so far, something like that, like associative array maybe can do something. So you grab some number, take the difference between itself and another number. The thing that's interesting is actually the differences themselves, like we want the next largest number and the difference between itself and the next largest number. Yeah, so that's kind of interesting. Well, if we look at, let's do like a smaller case. Let's do like 3 numbers. The first number, if it's not sorted, so the first number could be the smallest, and then you could find the next smallest number. So it would be the minimum difference, the minimum difference of all the numbers is the next number between itself and all the other numbers. And then between that number and its next number, same deal. The minimum difference between all the numbers that are larger than it. And of all of those, like that's a brute force approach that we could take, right? So we could say, yeah, take the smallest number, and then take a look at all the other numbers that are larger, which is all the other numbers, and then you really only need to look at one number, right? And take the difference. Now, we cannot sort this to do this. That's the tricky thing. If we sort it, then we hit an n log n bound. Like there's no way we can sort this. Yeah, we cannot sort this because of the n log n bound. No way we can sort it. So that means that if we do what we just described, we would inherently be sorting it, right? We would inherently know. Can we perform kind of like a binary search, maybe? Something like that. Yeah. How do we know that two elements are going to be next to each other in the sorted? Oh, you know what you can do? Oh, that's interesting. You can execute a intro sort to figure out which order statistic you have. So like the median, for instance, you could find the median, and then you could find the next number in linear time, right? I mean, even though you can do that using intro select or just median of medians on your quick select, even though you can do that and that's linear time, I don't think that answers this question. Because, like, if we were to sort our numbers, oh, now this is interesting. I think the largest difference between your sorted numbers, you can draw a line between. Oh, that's really interesting. This makes me think of like derivatives or something like that. Like if you made a function that returned the values in your array, if you sort the values, there's like a line that you can draw between the first value and the last value, and that's a monotonically increasing sequence or non-decreasing sequence. Monotonically non-decreasing sequence. What's interesting is the greatest variance is kind of what you're looking for. I don't know, man. I have no idea. I don't know. trying to figure out the maximum difference. If you knew the difference between everything else in, let's say it took linear time, well, you can't really do that in linear time, but if you knew the difference in everything else between everything else, well, we already said it's going to be linear, but yeah, we're going to visit every element already. I guess what I'm trying to say is, like, knowing this thing, does that imply that we also know how to sort this? No, not at all. So yeah, maybe you can do it in faster than n log n. Maybe you can do it in logarithmic time. I don't know. This really should be a gimme, but I don't know it. I don't know it. I don't know it. I want to say something like you could just take the raw differences and do something with that. How do they relate? I don't know. Kind of limited to just like associative arrays or just arrays in terms of what you can use, or some kind of a set. Maybe you could do like a sliding window type of deal. Maybe you can do like a I don't know. I don't know, man. So what's interesting about this is the difference between these two elements and it's in sorted order. So it's not the absolute difference, it's just the difference. Yeah. So that means we're subtracting larger from smaller from larger, right? That's important. So that difference is going to be the smallest. It'll be the negative numbers we just ignore altogether, right? That difference is going to be small. It's going to be the largest of the smallest, if that makes sense. So, so of all of the other numbers, when you take this difference, the negative values we don't care about. The positive values are the ones we care about. But it's going to be the smallest positive value, and then like if you did a round robin with all the differences from, take a number in the array and take the difference between all the other numbers, toss out all the ones that are less than or equal to 0, and then take the minimum of the positive values. That'll be the minimum, right, for that number, and then of all those numbers, take the maximum. Oh, is it that simple? Huh. That actually makes me think a lot about a dynamically. Yeah, that makes me think a lot about a dynamic programming problem. I think that's a dynamic programming solution. I think you can. I think that works. Let's try that. Let's see if we can just optimize that. Let's actually just write that out, see what that looks like, and then try to optimize it. I think that's all we need. That's super interesting. How do we do? 16 minutes? Yeah, okay, let's try it. So the way it works is going to be int ret. Excuse me, yeah, they said already this is supposed to be linear, but we're going to write a quadratic time algorithm. So for, well, we could do int I equals 0, i's less than nums. Now we're just going to say n, or ns, I don't know. Size. Okay. And now we're going to say int x start off with 0. So I went with the minimum that's positive. Something as simple as this. This should give you the answer. Now we're thinking if there's a way to optimize this. Nice. Interesting. Oh, okay. I guess not. I guess one of these is negative every time, right? If you're looking at 1 is the smallest. So if that's negative every time, then this won't give you the right answer. Is there a way we can get rid of this and still use this? Well, everything less than or equal to 0 we don't care about. And actually you could have all of them are less than or equal to 0, in which case that's the smallest value. Right, about that. Well, looks like we're not optimizing this one because it's not correct. B minus A. I don't know. What value should that be? Well, that should be a negative number, I think. Or just 0. You could do something like that, you know, if x is still that value, then just use 0. That, I don't think we should do that. Yeah, well, we know the difference can't be that, right? Okay, let's see. Just see if this is at least correct. I don't know, just set it to 0 or something. In some cases that'll happen. Don't really have a lot of test cases here, huh? So some random numbers, let's try that. Okay, I think we're correct. So our largest difference is 61. Okay. Huh. So another way to look at this is if you look at a sorted list and you say each successive number is another jump upwards, we're looking for the largest jump upwards, largest step, so to speak, in our, if our sorted list was a staircase, it's looking for the largest step in the staircase. Okay, I want to say, you know, I think this is actually the histogram question that we looked at already. I think this is related to that. I think you used a stack or something like that. Well, no, because we're not sorting the whole thing. They don't have the staircase first, right? It would be linear with no extra memory if we sorted the staircase first. The steps in the staircase are totally jumbled. I want to find the largest step in the staircase. All right, that's the scenario. Okay, I don't know the answer. I'm going to lay down and ponder it. I don't know. No answer from me. Just a guess. I don't know. Yeah, I wonder if this is related to the partitioning portion of heap sort, or not heap sort, quick sort, because you can partition, and everything to the left is smaller, everything to the right is larger. That gives you the ith order statistic, right? That's linear time. You can partition around a random number. You can also find what the largest difference is, or excuse me, when the values to the left, those are all going to be smaller. The values to the right are all larger.
take the larger values minus this value. The smallest of those would be that step that we're describing. So each number has a larger number, sequence of larger numbers, and the smallest of those larger numbers is what we want. And we can take the difference. So I don't know what numbers we could use that would be helpful here. What extra memory we might want to use. I'm thinking maybe a stack is what we want to use, stack-based solution. So like, I don't know, you push some number on the stack, and then you say, okay, find the difference. Push another number if it's larger. That's some difference that might be meaningful. This would be, well, that difference could be too big, right? I was gonna say we want there's like a very fine line that we're trying to move through here. Oh, this is a good question, man. We're trying to not simultaneously not I don't know. Not consider differences that are too big, but also consider differences that are the largest of the differences that are small. It's the largest of the smallest differences. That's what we're looking for. Huh. Could you find those smallest differences? Maybe we can make an array to find the smallest differences. So the smallest difference between the first element and the smallest difference between the second element, and so on. I mean, you could do that in quadratic time. Let's think about that for a minute. You might be able to do something with like an average number. Where every number has some difference from the average. Excuse me. And I don't think that helps us very much. No, it doesn't. I was thinking about drawing a line from the smallest to the largest, and then maybe that was maybe that's helpful somehow. I'm not sure how that helps us. Taking a stack is somehow useful here. I think before I had an unordered map back to an index. Maybe that's what we want. Maybe we want like every number maps back to an index where that's the best. That was the best difference so far. The smallest difference with that number so far. How does that work though? What do I have with that? confusing. I don't know if that's particularly helpful. You know what this makes me think of? This makes me think of the trapping rainwater problem, because we have non-decreasing and increasing sequences and things of that nature. We don't really know increasing or decreasing the sequence of differences. We do know like the sequence of smallest differences. We do know the differences themselves would be an increasing sequence, like for a particular number. So for a given number, the differences you might have would give you an increasing sequence. What's interesting here is if we knew all of the smallest differences, then we could take the smallest number and sort the list. So we can't actually know all the smallest otherwise we could regenerate the sorted list. We can't actually know all the smallest differences. We can know the so this can't be done in linear time. Actually, I think that's a proof, because you don't know what all the smallest differences are, you can't know what the largest one is, because the next smallest difference you consider could be larger than the largest one you've seen so far. And so because you need to know what all the smallest differences are, is that true? That this is not possible? Am I crazy? Because you can't know what all the small, because you can't know, yeah, so you can't sort faster than n log n time by comparison. I mean, there's like a certain computational model, but assuming that model, we're using that model, I guess. Can't do better than n log n bound on sorting. And so the problem is that if you knew all of the smallest differences, you could find the smallest number in the array in linear time, and then use the smallest differences to sort the array, to regenerate the sorted array. Now, no, that's not true. You couldn't do that. I take it back. I'm wrong. That's not a proof. Because you don't necessarily know what the smallest differences are. You don't know what the order is. In other words, those smallest differences have an order with respect to the original array. Okay, never mind. No, we're fine. We're okay. But yeah, so the trade-off is you're going from n log n time and constant space to O of n time and O of n space. I don't know, man. I think I figured this out a while back, but I didn't remember how to do it. I do think I did this a while back, and I just don't remember how. Linear time and linear space. How do we do that, man? I have no idea. I'm thinking of a DP solution. It's got to be a DP solution of some kind. All right, how about this? What if we solve it for the n-1 case, and then we consider the n case. We introduce another number. Let's say we solve this, and we introduced a new number. So if we solved it and we introduced a new number, we would need to know what the differences between that number are or is. Oh, uh-oh. Headset's dying. Oh no. Oh man, I got stuck on this problem. I got stuck. This should be like an easy like data structures question. Headset's dying, man. It's dying. Excuse me. Excuse me. How are we doing on time? My headset's about to die. You get like a few minutes when it starts beeping. But it gets very close to dying. Alright, how are we doing? There we go, great. Okay, whoa. Okay. The problem that we have is... Oh boy, oh brother, oh brother. It's a challenging question. Let's keep thinking about it here. So, linear time, yeah, yeah. I know I've seen this before too. I know I've seen it before, how to do this. I really do think it's got something to do with like the histogram question that we looked at before. Or just some kind of stack-based solution. It's got to be a stack-based thing. It's got to be. There's no way it's not. Oh, I have an idea. Okay, I have an idea. So, all right, let's do it this way. So we see a number. We see another number that's larger. Take that difference. See another number that's larger again. Now it's somewhere, it's either larger than the first or larger than the second, right? If it's larger than the second, then there's that difference to consider. But if it's smaller than the second, then we can take that difference, pop the larger one from the stack, and yeah, okay, it's got to be a stack-based. Yeah, it's got to be some kind of stack-based solution. I'm like way overthinking this. The reason is that the differences that you come up with, if you have a smaller number than the number that you've considered already, we don't care about that difference. So we're trying to get the largest of these smaller differences, but yeah. So we're not just minimizing the differences altogether, which is kind of a subtle thing. Trying to actually minimize and maximize at the same time simultaneously. If we just minimized in both cases, I think it would be pretty easy. I think we do that in linear time actually. Can we? Let's try to do minimum and minimum. Let's try that. The smallest of the differences. Well, I don't know. What would that look like? If you took, I think you could use a stack for that. It's just every difference we see, we want the smaller one, right? So take a number, and you have another number that's larger. Take that difference, you get some number, and then you could pop the smaller one. No, not pop the smaller one. Take another number, and that's, let's say it's larger, so you take that difference and check it against your current value. I think you do this in linear time and constant memory, extra memory. Oh no, sorry, it's not constant extra memory, it's linear, yeah. And you just keep comparing against this against this difference that you see, and every time you compare differences, you want the smaller ones. The larger numbers, you never need to compare them against the smaller numbers because they're larger, obviously. But the smaller numbers, you want to bring them down to compare them to numbers that are smaller. What's weird about this, though, is that if you see a smaller number and you pop all the larger ones off, any larger number that you see should have been compared to one of the larger ones. Like, in other words, you see like 59, you see like, I don't know, 40, 45, 50, 59, and then you see 60, or you don't see 60, but then you see 41. You would pop 41 all the way down. When you see 60, you're going to have something of a problem because 60 was larger than 59, and it was closer to 59. So you wouldn't want to do that. So actually, I could be wrong about the minimums. Maybe actually you want the maximum of the minimums. Well, yeah, you still would have an issue because if you saw 60, you'd see it. Yeah, no, you're actually just not seeing enough of the differences that are possible for that to work correctly. I don't know, man. Why does sorting get rid of all of the it gets rid of so many possibilities. Excuse me. I don't know, let's look at the quadratic algorithm. Maybe that's easier to think about. So if you were to just it's getting kind of late too. If you looked at the quadratic algorithm, if you were just to do what? Take a number, compare it, get the difference between all the other numbers, the ones that are, that's actually what I did before, right? All the other ones that are larger. And take those differences and take the smallest of those differences. Actually, what you can do, you know what I want to do? I'm thinking about it. You could just you could initialize to the first difference. That's what I was thinking. And then take the minimum of all those differences. No. That's awkward. I actually don't know. My quadratic algorithm's got some issues. So if you take, what kind of sentinel value can I use for this to make sense? We could set x to -1. No. That's really awkward. Yeah, you can't just pick a random negative. You can't just pick a random difference to set the value to. You can't even find a random positive value to set it to, like, because it could be the case that none of these, there are no positive. It could be the case that there are no positive. You know what you could do? You could have it uninitialized and then just have a boolean set or unset. I've done that before. And if it's not set, if it's set, then you can count it. If it's not set, don't count it. That's how I've done it in the past. Let me see if I can try that. Let's give that a shot. I don't know if I can optimize this or not, but I can at least have my algorithm be a little bit more, like, not consistent, but I guess reasonable here. Bool has set, or I don't know, just check equals false. And we'll say if d is greater than 0, so we can do something like this. We do if not check. We'll say, we'll do something like this. So if d is greater than 0 and not check, well, yeah, we can do that. Yeah, let's do it this way. If check, otherwise check equals false or true, or I don't know what to name this variable. Is set, has been set. C, B, we'll call it B. B is fine. Boolean. Boolean to true, and x equals d. So, and we just say if d or b, then yeah, that's more of what we should be doing. Oh, I did that wrong. I don't know, B. I want to, what's a good name for a Boolean for a check? Guard or something, or not guard, but has been set, is going to be set, currently set, touched, untouched, open, locked, guarded, closed. I don't know. Initialized. I don't want to use I. Could just say alpha. Just Greek letters. That's kind of what I've resorted to over time. I'm like, I don't know what to name these variables anymore, man. Start using Greek letters because they've got such like specific meaning, and it's like hard to express exactly what the meaning is of these variables. Yeah, there you go. It's better. But can this be optimized? Is the question. Well, not really. Can we store something somewhere? Maybe we can store the differences at certain indices. So I think it's got to be a stack-based solution, but maybe I'm thinking like at different indices, what we can store is like for a particular number, the difference between that number and something else, and then you would keep
making that difference smaller and smaller as you see more numbers. But the problem is that we're not updating the whole array. We could use an interval tree, but interval trees are logarithmic, not constant per update. So I have to charge the headset. That doesn't really work. Doesn't really help us. But an interval tree would be useful here. Who knows, man? Who knows? This is a challenging one. I don't know. I don't have the answer to this one. Oh boy. Oh, it's gonna take me a long time to get through all these problems, huh? Isn't it? It's gonna take a while, huh? What could it be? I'm thinking stacks. It's got to be some kind of a stack. So what if we? Excuse me. What if we do only smaller elements on the stack, and if we see something larger, then we don't push it on the stack? I don't know if that makes sense. Can we use a queue maybe? I don't know. Do we want to put anything onto a stack? What do we do? What do we do? Well, I mean, you can maintain a sorted list, quote unquote sorted list, using a stack from left to right, where you can pop off all the larger elements as you add each element. Excuse me. But I don't know that helps us very much. Like, why would you want to do that? At least for this case, this problem. The differences that you get are not necessarily all that meaningful. Kind of thinking it through in my head.
what was I thinking here? What was I doing? I was trying to imagine how a stack could be useful here. I don't know, man. I don't see it. I mean, a stack is just also recursion too. You can think about it as recursion. No, that's not true. That's not true. I shouldn't say that. No, it's not. No, I mean, yeah, recursion stack is useful, but stacks and recursion stacks are very different from each other. They're not so easily interchanged. I wouldn't do that. I wouldn't say that. I used to think that you could do that. Like in theory you can, but in practice it's a little bit more challenging than that. What are we thinking here? Maybe you could use a queue. Would that be helpful? I don't know, man. Oh man, I'm struggling here. I don't know. Gotta keep thinking about it. Man, I got stuck on this one. I don't know. Maybe we'll just make this a part 1 and call it. Sleep on this one. Yeah, it's probably best. I mean, I think I got stuck on this one. I would say it's fair to say that I got stuck. I really think it's some kind of queue or stack-based solution. Linear time. I don't know, man. That seems just hard. Oh. Oh, no, I was thinking maybe some kind of heap or something. But no, insertion into the heap is logarithmic, and popping with the heap is also logarithmic, so no. It's the largest of small numbers. It's 2 dimensions you're comparing. One dimension is differences between this particular index and the other differences in the other indices. Well, I mean, you could think of it that way too. You could have like an array of arrays, like a matrix of all the differences. And on one row is all of the difference with a particular number, and then on another column, and yeah, and then you could do that. And this would be like indices. And then you would take the minimum positive number from each row. It's kind of what I'm doing in my loop, my nested loops here. And then taking the minimum of each of those results. Or excuse me, the maximum of each of those results. Okay. Can maybe use sort of like a sliding window type of deal where you have the smallest value you've seen so far simultaneously with the largest, smallest value you've seen. So everything that you need to consider needs to be larger than that. But also the smallest of the differences you've seen. So your differences need to be something like that. Like there's a bound that a bound above and a bound below. Where every difference needs to be smaller than the upper bound and larger than the smaller bound. Yeah, the smaller bound would be the smallest. It's not the smallest difference you've seen. It's like of the differences with a particular number, you want to be larger. Sorry. I don't know. It's challenging. This is challenging. maybe the stack could be of the smaller of the minimum differences. Each time you see a minimum difference, you could push that onto your stack, and so that would be monotonically increasing. But I mean, really, actually, that you could eliminate the ones that are below altogether. Well, the other values you don't necessarily know if the difference you see, if that's a larger difference or there's also something to be said about like connecting differences between each other, something like that, where there's like a transitive, oh, maybe that's what we're supposed to be doing. There's like a sort of a transitive quality where if you have A, B, and C, you take C minus A and B minus A, C minus A minus B minus A gives you C minus B, right? C minus A minus C minus B gives you say B is larger than A. No, let's say A is smaller than, A is smaller than B. Yeah, then you get B minus A out of, right. Oh, that's interesting. So you can take the difference between two differences and get another difference to consider. Huh. Oh, that's interesting. That helps us, I think. It's kind of what I was getting at before with the triangle inequalities, I guess. Well, it's not a triangle inequality, but it's a transitive difference. So you could actually take differences of differences and get those other differences. So now if you consider a difference between two differences, you take three random numbers, right? And I guess you could sort them and take the differences there, but let's say you didn't sort them. Can you get the largest difference between those numbers? Well, you could take the difference between the two largest numbers and then, no. I guess you could say something like, well, I don't know. Excuse me, well, if you had A less than B less than C, you took the difference between C and A, and then then you had a difference B and A, and then you took the difference between those two differences. So it's A minus C and A minus B, and then A minus C minus A minus B. Excuse me. A minus C minus A minus B. gives you negative c plus b, or b minus c. So you take the smaller, which is the larger difference, and subtract the other difference. So if you take the difference between two differences, one larger than the other, then you'll get yet another difference, which could be smaller than all the differences between, I guess, b and all the other numbers. Really, it's the largest positive difference that we're looking for. So that's interesting. So you can take, oh, that's really interesting. Okay. Yeah, maybe the stack-based solution is what we want. So so you can do A to B, take that difference, right? Two different numbers. And suppose they're, that's interesting. Huh. Do you want to put differences on the stack? Well, the differences need to be between like the same numbers, I guess. Yeah, if you're going to do that, you need to have the same three numbers, I guess. In other words, you want to make sure you're always dealing with the difference between two numbers. You can guarantee the difference that you're looking at if you take a look at two different differences, one smaller than the other, and you take their difference, right, and they have a common element. Say A minus B, and let's do B minus C and A minus C, right? So B minus C minus A minus C gives you B minus A. B minus C, B minus A minus C, yeah. Oh, that's confusing. Excuse me. What does that tell you, though, if you take two differences between the same numbers, so like A and A minus A to B, and so B minus A and C minus A, where A is less than B is less than C. B minus A, C minus A, C minus A minus B minus A gives you C minus B. And that C minus B, so that would give us your B minus A, your C minus B, and which of those two is larger? So B minus A, B minus C, one of those is bigger than the other. If B minus A is larger than B minus C, that means C is larger than A. Oh, I see. Yeah, you can compare those two numbers, those two differences from B, and the smaller one corresponds to a larger number being taken away, which would then imply that that larger number being taken away, you could take the difference between that larger number and the other number, and you can get that difference of that larger number that was being taken away between the larger and the smaller. Oh, I see. I don't know how useful that is for what we're doing, though. It seems like it might be. I think I should make this a part 1 and go to sleep. I think I'm really tired. I don't know if this is actually useful, what I'm describing here. I guess what I'm trying to do is I'm trying to set up a... No, that doesn't work either. I mean, maybe we can, if we took all of our differences, all the differences that we have between all the numbers, we created a graph. Maybe there's some way we can traverse this graph. Maybe that's what we want to do, something like that. Excuse me. And what do we want to find in this graph? We want to know this one particular node that we're trying to find. And that node is the largest of the differences, of the smallest differences, where these smallest differences you're comparing against are, for a particular number, the differences between all the other numbers, the smallest of those differences. Each number has its own smallest. I want the largest of all those numbers, small numbers. I don't know, man. I don't know the answer to this. Definitely not. For some reason, I'm thinking processing the difference array would be useful. I don't know. I don't know why I think that, though.
Maybe what we can do is say, if our difference is larger, so calculate some new difference. If it's larger, we want to compare it against the difference we currently have. But we also want to check if we can reduce that value, if it's the small, if we should be comparing, if it is the smallest we should be comparing. So I guess there would be two numbers that we're looking to compare to each other. And yes, we're trying to find two numbers, right? We're trying to find one number that is the first half of the pair that we're looking for, and the other number is the other half of the pair. One number is larger than the other. They're actually going to be next to each other in sorted order, and they also have the largest distance between the two of them of any two numbers that are next to consecutive in the sorted order. That's really what we're trying to do. We're trying to find both of those numbers, both that pair of those two numbers. And I guess what you could say is, I guess what you want to do, so, could do something like maybe have a map, a hash set associative array where each number you're going to keep track of the closest number, the closest, smallest, largest number you've seen so far for that number, something like that. And I don't know, like you see a number and you see another number, you take that difference, or not the difference, but you could say for the first number and the second number, or the first number you've seen this larger number, or vice versa, depending on which one's larger. Then you see another number, and you say, okay, compared to the largest number I've seen so far, if this is larger, then we can kind of update those values. And maybe you see a smaller number. I don't know. That doesn't seem very useful. Doesn't seem like the way to do it. I don't know, man. I don't know how to do this. It's challenging, really challenging question. I don't know. You're looking to somehow. It's quite the brain teaser. Quite the mind-bending question here. I don't know. Excuse me. I don't have a clue. I am totally lost on this one. I think I need to go to sleep. Yeah, I'm just straight up guessing what this could be. Outright guessing. All these negative numbers we can ignore, right? So it says you find a number that's larger, you could take that difference. A smaller number, we can take the other difference. We can reverse the numbers and take that difference. Hmm. Hmm. Yeah, I'm falling asleep over here. I can't think of any solutions. I don't know. It's got to be some kind of trick that I'm missing here. Well, I don't see anything obvious. Linear time and linear space. What would be the linear space? Why? Some kind of a stack or a queue or something? I was thinking an unordered map. I mean, a hash, an associative array or an array seems like the most probable and useful thing here. It sort of gives us the most reach, the most information to work with. I mean, I'm thinking a graph is like a really natural analog here because we're comparing each node to every other node, and I guess those could have like weights or something. Excuse me. Yeah, you could make like a graph, a weighted graph maybe. Edge, the weights of each edge would be the differences between the nodes. And every node has an edge to every other node. And I guess the minimum spanning tree, minimum weighted spanning tree would be exactly the like, I guess it would be all of the edges that are the smallest differences. That those would be all the successive edges as described. That would also be a path. That would give you a path all the way through the graph, and you're looking for the largest weighted edge on that graph. That's what it comes down to. So I guess what's interesting about that is that would split that spanning tree into two smaller pieces. Excuse me. Well, actually, that edge could kind of be anywhere on that path, but that's what you're looking for. If you can compute that minimum spanning tree efficiently, which I think you can. I think you could compute minimum spanning trees in linear time. I think the way you do it is you just take, I think it's a greedy algorithm. I think you just take the smallest edges, right? So, yeah. Smallest weighted edges. Excuse me. Does it matter what edges you take for a spanning tree that's not weighted? I mean, you can take random edges as long as it's an edge between a vertex you haven't seen already. Yeah, okay, interesting. But how do you get the... Well, that's kind of the problem, right? I mean, we don't know how to easily determine what the smallest. Oh, that's interesting. Huh. Well, that would. I mean, I was going to say, can you efficiently find what the next closest element would be for a particular number? I don't think so. Because that would give you your greedy algorithm. Excuse me. But wouldn't you get a sorted list if you did that? A to B to C to D, etc. Like each successive element would actually just be the sort. Is there a way we could do this without necessarily knowing all those things? I guess what you could do is say, for each element that you add to your set, so you have a set of numbers, or I guess nodes in your graph, each one that you add, you want to I guess you want the smallest weighted edge each time. But what's interesting is that you can as you add nodes, you can replace the edges between the nodes that you already have. So let's say, oh, that's interesting. Oh, I could do that. Yeah, that's kind of what I was thinking before. Like, okay, each, so you can store that in a hash map. Each node that we've considered, we have it connected to another node, right? If we add another node to consider, we can take the optimal difference, the optimal edge to that node. Yeah, I guess we're kind of stuck just looping left to right through all the nodes kind of randomly. But we have n edge to that node. There may be a smaller edge that we could add. So we create our path, we can create a better path or a different path. Yeah, ultimately we're just rearranging the connections that we have in our so what's interesting is excuse me. I don't know, man. I'm running out of ideas here. a quadratic algorithm would be like, you know, we have these three, we have a node, add another node, we have an edge between that node, we add a third node, we want to check we want to take the minimum of the edges of those three nodes. So it's basically sorting those three, and we can do that. And then we have another node, and we want to take, it's kind of like a nearest neighbor type of thing. We want to connect that node to the nearest of those three numbers to that node. Which is kind of like a logarithmic search, you know, binary search. Don't really want a binary search, but that's kind of like what we could do. You could do a linear search to do that, or a binary search, but you could find the node that would connect. The shortest path, and you want also of those shortest paths, you want the largest each time. And then connect another node. Again, the shortest of all of the paths that you have so far. You also, like, I guess you'd want to update all of your connections and your paths, because your connections, because adding another node, you know, the other connections might be better connected to that node. I don't know, man. I don't have any ideas. Alright, let's just say I got stuck at this one. And move on. I'm gonna go to bed. I think it's time for sleep. I've been thinking about this for a while now. I don't know how long, but it's definitely been like quite a while. I don't have the solution. This one's 2 hours now. Oh boy. Oh man. It's like 10:30 now. Hello. Just came to say I'll see you later. Oh, I'm sorry, Melito. I didn't realize you were here. I was laying down. Alright, anyway. Alrighty, I'm gonna make this a part one. I couldn't figure it out. Spent 2 hours thinking about it. Challenging. Yeah. Thought about all kinds of stuff, but didn't get there. Okay. Alright, so let me end it here. So yeah, I don't know. I couldn't think of anything. Is that really right? The problem is it integer array on nums return the maximum difference between two successive elements in its sorted form. The array contains less than two elements, return 0. Write an algorithm that runs in linear time and uses linear extra space. Yeah, I couldn't get it. Yeah,
linear time and linear extra space. Couldn't figure it out. There's got to be some kind of trick to it that I just don't realize. All right. Thank you for watching. Talk to you soon. Have a nice day.